Good evening, everybody. I'm Arun Rajkumar, and I'll be talking about a differentially private stochastic gradient descent algorithm for multi-party classification. So in today's world, a lot of data is available often across parties, and it becomes essential for these parties to collaborate with each other so that they can make better sense of the data that they have. When I say parties, these could be multiple social networks which will want to collaborate so that they can give better user ad recommendations and so on, or these could be banks which have financial data about users and they would like to collaborate so that they can come up with better financial parameters. Or these could be, for instance, hospitals which have sensitive medical information, and then they would want to collaborate so that they can come up with better diagnostic procedures and so on. So the point here is that in most of these cases, sensitive data is often available across multiple parties, and it becomes necessary for these parties to collaborate with each other in a private manner, in a privacy-preserving manner. So in this talk, we will focus on private algorithms in the multi-party case, but then privacy is, to get a formal notion of privacy, we will use something known as differential privacy, which was proposed recently a few years back, and then we'll try to see how this notion, the strong notion of privacy kind of fits into machine learning framework and what we can do in the multi-party case. Okay, let's start with a simple intuition for what differential privacy means. Let's say we have a database D, which has, say in this case, 3 users, user 1, user 2, and user 3, and there is some sensitive information about this user, about these users in this database. For instance, this database could contain, say, the salary information of users in a city, and then, for instance, you would want to release to the public the mean salary of the city. So what you want to achieve is that just by computing the statistics, but just by knowing what you release to the public, nobody should be able to figure out what is in this database. So differential privacy tries to achieve this by making the output of the algorithm that runs on this database to get a statistic randomized. By this I mean that you run some algorithm on this database, randomized algorithm on this database, and then you get a probability distribution over the output that you are actually releasing. In this case, for instance, it could be a Gaussian centered around the mean salary of the city. Differential privacy now says that if there is one more database D dash which has one extra user, in this case U4, and then you run the same randomized algorithm on this database, the output distribution that you get should, in some sense, should be closer to the output distribution that you would have got if this 4th user was not in this database. So what this would guarantee is that the user U4 in this case has a bounded risk of participation in this database. So irrespective of whether this user is in the database or not, the output distribution would kind of remain similar. So this is the intuition. The formal definition is the following. A randomized algorithm A is known to give epsilon differential privacy if for all datasets D and D dash that differ by a single element, and for all S which belongs to the range of the algorithm that you run on this database, the probability that you fix an output in the output space, and then you look at the probability that this output would have been got from database D and the output could have been got from database D dash, and then you compare these ratios, and these ratios should be small. It should be bounded by e to the epsilon. For instance, if I pick a particular point on the output space and then I compare the ratios of these distributions, they should be bounded, and this should happen for every point in the output space. If you have such an algorithm, then that algorithm is said to be epsilon differentially private. So as you can see, this notion is kind of generalized. It does not, when I talk about differential privacy, this is any algorithm can be made differentially private, but then what we are interested is the case to see if machine learning algorithms can be made differentially private. So the setting that we look at is the basic binary classification setting, which all of you must know. So you were given a set of points, x1 with labels, and what you want to learn is basically a function which from x to y. So this is, the function in this case, let's say it's linear and is characterized by a vector w. And this function, this W can be got, for instance, by minimizing a regularized ERM objective. So the question now is that, can we make this output private? Can we release a differentially private version of this output? And if so, how? So this question has been considered before, and there are two basic techniques which kind of work for achieving differential privacy in machine learning, which are kind of popular. The first one is called as output perturbation. In this case, what you do is you minimize the regularized ERM objective J of W, you get W star, and then you perturb it with some noise eta. If it can be shown that if this noise is of the distribution, it's Laplace distributed with certain parameters, then the output can be differentially private in the manner that is, it satisfies the definition that I showed before. So there is one more method which was recently proposed by Chowdhury et al. In the JMLR paper. So it's called as objective perturbation, wherein instead of perturbing the output of the algorithm, what you perturb is the objective that the algorithm minimizes itself. So in this case, what you will actually be getting is a minimizer of an perturbed objective. In this case, if you see, there is an 1 by n W transpose eta in the objective, but this eta is now chosen in a certain way from some Laplace distribution with certain parameters. So what we are interested is in the multi-party setting. So the setting is simple. So you have different parties. The data set is basically divided into k parties, and then what each party wants to learn is a classifier which makes use of as much data as possible, if possible the data from all the parties, but at the same time protecting the privacy of its own data. So what you're also given is a third party which can kind of collaborate, which can communicate with these parties. So in this setting, can we make algorithms that we already know differentially private is the question. So this question has been recently considered in a NIPS paper in 2010 by Pathak et al. And they propose a very simple solution to this. What they say is each party computes its own local classifier Wi, and then the third party aggregates these classifier, averages it, and just perturbs and gives a noisy version of this aggregate classifier. So it can be shown that this aggregate classifier achieves differential privacy for certain parameter of eta, which is Laplacian also. It also requires a secure cryptographic protocol, because the third party in the process of aggregating and perturbing should not also gain any information about any of the parties. So they use a secure cryptographic protocol based on homomorphic encryption to compute this vector W out. The question is, so this seems very simple, and but it seems that computing each individual classifier and then combining, rather than combining them, if there was a method which could directly combine all the classifiers together at the same time achieving privacy, then that probably could be better. So this is the motivation for a new algorithm that we proposed in this paper. So the function J of W, which is the regularized ERM objective I mentioned before, is separable among the k parties. What this means is that the third party can basically obtain gradients from individual parties and then combine them and then basically run a kind of a gradient descent algorithm on the objective. And what we expect is that because you are optimizing on the entire objective, this should intuitively perform better than the previous algorithm. But the big question is, how do you achieve privacy in this case? So let's try to attempt achieving privacy in this case. The del J of Wt is the gradient of the regularized ERM objective written in a slightly different way, wherein I have indicated the gradient as a sum of gradients over k parties. Now if each party computes del GKWT, which is the part of the gradients corresponding to its own data set, then the third party can basically average these gradients and then compute the gradient of the entire data set at any Wt. So the question is, every time when each of the parties is sending their gradients to the third party, these have to be private. So will it be possible if each third party, when it is asked for gradient at Wt, if it adds some noise, say rho tk, where k corresponds to the kth party and t corresponds to the tth iteration, which is proportional, which preserves privacy of the gradients, this seems to solve the problem. But unfortunately, this is not enough, because now what the third party can be seen as doing is kind of saying, what we are doing is now the third party is kind of getting noisy gradients, and it is well known that as long as the gradients are zero mean and finite variance, the third party, even if it uses a noisy gradient, and because these gradients are IID samples, I mean these noise vectors are IIDs, the third party can still converge to the local minimizer of the entire objective, and that would not be private. The output finally you get would not be private. So what we do is make another attempt at solving this problem. So now each party, instead of adding the noise that preserves its gradient, which is a variable noise which is added at every iteration, it also adds one more noise which is a fixed noise. What this means is that this fixed noise, the effect of this fixed noise cannot be taken away by the third party. So because it is the same noise that gets added to every iteration. So if the third party now runs a gradient descent algorithm, for instance, on the noisy gradients that it receives, what it would basically be minimizing is an objective perturbed version of the regularized TRM. So if you look at this, so this is exactly the same objective except that there is a noise term that gets added. And this looks similar to the objective perturbation that I described before, except that the noise is a summation over k terms, k parties, and unfortunately, if each of these noises are Laplacians, then Laplace distributed, then the summation would not be Laplace distributed, and so the same privacy that you had in the objective perturbation case cannot directly apply here. So the natural question is, you want some noise which ones, when you sum as well, will be the same form. So would the Gaussian noise work, would be the next question. So it does work, but with a modified privacy guarantee though. So this guarantee is known as epsilon delta guarantee. What this says is that your algorithm is epsilon differentially private with high probability, with probability 1 minus delta, which means over your output space with probability 1 minus delta, if you land on an output, you would be epsilon differentially private. So, and this is a slightly weaker form of privacy, but then it works for Gaussian vectors. So if you can, in fact, use this method and then make the algorithm that I just described above epsilon delta differentially private. And as I said before, this algorithm can now just be viewed as Gaussian perturbed objective, and then you can analyze the algorithm as just objective perturbation but with Gaussian noise. So, okay, so this is just the algorithm which I skipped. So this is fine. So we are releasing some classifier which is the perturbed version, but then how useful is this classifier? You might as well release random noise and then still say you're preserving privacy. There has to be a notion of utility, and well, in differential privacy, general idea is to fix some privacy parameter and then see what is the utility you get out of this privacy parameter. So, so this is now I'm going to compare the privacy and utility guarantees of our algorithm with the simple algorithm that I stated before, so which is the local aggregation, wherein you just combine classifiers from different parties. So their algorithm achieves epsilon differential privacy, but then we achieve a weaker form of epsilon delta differential privacy. However, if you look at the utility guarantees, wherein the excess risk of the output that you release, W out, with respect to the best possible classifier that you could have got if you had used all the data points together, depends on two terms, which is K, which is the number of parties, and N min, which is the minimum number of data points with any particular party, which is in kind of says the skewness of the data distribution across parties makes the bounds weaker. So, however, this is not the case with our method, which is kind of also intuitively clear. It does not depend on the number of parties, neither does it depend on the minimum number of data points, whereas it depends on the total number of data points that you have. So this is the advantage in the sense of utility that we provide of the output that of the algorithm. So we did do some experiments to check if the bounds that the theory states are in fact hold true. So the first experiment was with synthetic data, wherein we generated points uniformly from the interior of a hypersphere, and then we fixed a classifier when we wanted to check how these methods perform when you have, say, 1,000 points, I think, in this case. So the first plot I'm showing is the effect of the number of parties with the test error. How does it affect the test error? The light gray ones is our algorithm, and the dark gray ones is the previous algorithm that I said. As you can see, as the number of parties grow, the test error kind of goes up. And this is both in the case of epsilon is 0.1 or 0.2. Though I should mention, in our case, we should set a delta parameter, wherein it was not there in their case. And the delta parameter we set is 0.05, and which means you are 95% confident of what happens. The next experiment we did was to test the skewness, which also the theoretical bound stated. And here the x-axis corresponds to the skew vector. 1 says the data was divided equally among parties. 2 says the party that had the least amount of data had 10% of the entire data set. And 3 means it had 1% of the entire data set. And as you can again see, the skewness indeed affects the test error. So we also did similar type of experiments for real-world data sets, which is the breast cancer data set, wherein it's a binary classification task, wherein you had to say whether the tumor is malign or benign, and the results kind of are similar. In fact, the loss, increase in test error seems even more in this case for the previous algorithm, whereas our algorithm is kind of more robust to this. In summary, I've presented an epsilon delta differentially private algorithm for the multi-party setting. This achieves better generalization bounds. You can use the theorem that is stated to prove generalization bounds as well. And we experimentally verified the performance over previous method. Thank you.
Plenty of time for questions.
So you've shown how to protect against the third party trying to find out information about people. But what about cases where, say, there's some of the people participating in this scheme are collaborating with the third party to sort of together try to extract information?
Okay, so that's a good question. So in this case, what we're assuming is each of the parties is going to add the noise that we want them to add. So, but if the players are rational, so that needs separate analysis. So, which is not done, at least in this work. So, yeah. So we did think of it, but that is not done, at least in this work. Yeah.
On the last couple of slides, dealt with the confidence you have that you're maintaining privacy.
Right.
Yes. So, how did your classifier perform if you had delta very small?
Well, yes. So we made delta as small as 0.05 to 0.01, and then the parameter delta does not really seem to affect it much, whereas the parameter epsilon is where the effect is seen more. So which is like if you need stricter privacy guarantees, then for instance, if you need 0.01, if epsilon is set to 0.01, then there's a problem because the noise that you add is directly inversely proportional to epsilon. So as you reduce epsilon, the noise level gets increased. But then delta does not seem to really affect as much as possible. I should also mention that in practice, you can set epsilon, you can say this is the epsilon delta that you need, and then the parameters will automatically be tuned according to what you need. Yeah.
Any more questions? Presumably your algorithm can be extended to any optimizer that deals with separable functions such as neural networks.
Exactly. Exactly. Yes. Yeah. And we also want to see if, how this would work if you have a network wherein there is no centralized third party, but thing is decentralized and each node can communicate only to its neighbors, and then how the structure of the network would then affect the privacy guarantees would also be interesting to see. Yeah.
If I understood it correctly, you are assuming that each party has access to one subset of the points, right?
Right.
Have you considered a situation where each party has access to all the points but only some attributes?
Well, no, that has not been considered. This is, yeah, so that is not considered in this case. Yeah, that would be interesting as well. Yeah. Sure.
Any other questions?
Okay, then let us thank the speaker again.